Welcome everyone. This is the video solution for CodeForces Global Round 28. Global rounds are usually due to contests. So I'm going to discuss from the problem A to D. So first I will just list out the difficulty rating of each and every problem. So I would say A is around 800 to 900. B is around 1000 to 1100. C is around 1200 to 1300, and D is around 400 to 600. So comparatively D was a pretty easy problem for comparison to all the due to D's. So let's move to the solutions of all these four questions. So starting with the first question, let's understand what the question says. Kevin is trapped in Lakeside village by Grace. At the exit of village, there is a combination lock that can be only be unlocked if Kevin solves it. The combination lock starts with an integer x. Kevin can perform one of the following two operations 0 or more times. So the first operation says, if our x is not equal to 33, he can select two consecutive digits 3 from x and remove them simultaneously. For example, if we have x as 13323, we can remove the second and third 3 and change it to 123. That means second and third 3. We will take this 33 and we will remove it from the string, and our string will be 123. Our second operation is, if our x is greater than or equal to 33, he can change x to x minus 33. Our second operation says, if we have a number which is greater than 33, we can change it to x minus 33. For example, if we have a 33, we can change it to 0, 34, 1, 66, 33, and then 0. This is our second operation. Now let's see what the question wants. When the value of x on the combination lock becomes 0, Kevin can unlock the lock and escape from the Lakeside village. Please determine whether it is possible for Kevin to unlock the combination lock and escape. So we want to find out if our x can be reduced to 0 or not. If it is 0, then Kevin can escape from the Lakeside village. Input is our test cases t and the only integer x. Output as if it is possible for Kevin to escape, output no if it is not. So moreover, our question is, using these two operations, we want to reduce our x to 0. If we can, then print s, otherwise print no. So let's understand some sample test cases. Our first is 165. So 165 does not have any 3 3s in it, so we cannot perform the operation 1, so we will go for operation 2. Minus 33, we get 132, still we don't have any 3 3, so minus 33, we get 9 9, minus 33, 66, minus 33, 33, and in this we can choose any of the operation. Either we can remove these and make it 0, or we can minus 33 and we get 0. So yes, we can change our 165 to 0. Second test case is 6369. First, what we can do, we can minus 33, we get 6339, then we can remove this and we get 69. After removing 66, it is not, we get 6336, then we remove this, we get 66, and 66 can be reduced to 33, and 33 can be reduced to 0. So if you understand what we have as our operations, the first one is to remove the 33 from the string or the number. Our second is we can reduce it to x minus 33, and we can perform this operation 0 or more times. So let's take three examples. Let's say we have our x as 32, x as 33, and x as 34. Let's see what happens in this case. In 32, the only operation we can do is this, but we don't have 33 in the string. So this 32 will remain as 32. 33 can be reduced to empty string or 0, or it can be reduced by minus 33, so we get 0. In 34, the only operation we can do is this, minus 33 we get 1, and this one will remain 1 as it is. So if you understand, if it is 33 at some point, it can be changed to 0, but if we get a number where we around from, let's say, 1 to 32, from 1 to 32, we cannot change it to 0. So what happens when we in 34 we get 1 at some point. So if we have a number between 1 to 32, we print it. So what do you mean by 1 till 32? And if you see, we are reducing the number by 33. So it is nothing but, if the number is 33's multiple, we can reduce it to 0. 66, 33 minus 33, 0. So 33's first multiple is 33, second is 66. So if the number is divisible by 33, we can change it to 0. But if it is not, then we have a remainder. The remainder will be nothing but in between, from 1 till less than 33. That is nothing but in between 1 to 32, inclusive 1 and 32. So we just have to check if the number is modulo 33 or not. What do you mean by modulo? If we get a remainder, that means the number is not a multiple of 33. That means no. If the remainder is 0, then yes. This is more over the logic. Why we are not considering this operation? Because this operation is already covered in this. We can also change if our x is 33 to 0. Due to this, we are able to perform this logic because this possibility has been covered by second operation itself. So that is more over the logic of this question. So let's see the code. So the code is very simple. Let's take the input of the t's test cases, and after that we have our number, and if the number modulo 33 gives remainder 0, then we print s, otherwise we print no. Pretty simple. Now let's move to the B question. So our B question says, Kevin is a master of permutation related problems. You are taking a walk with Kevin in dark woods, and during your leisure time, he wants to ask you the following question. He will ask you one question. Given two positive integer n and k, construct a permutation p of length n to minimize the sum of the minimum values of all subarrays of length k. So this is very big statement, and we have something of something of something. So let's break it down. I know this sounds pretty complex from this particularly. Let's see. And we have a mathematical equation. So this is pretty complex to see, but it is not. Let's understand how. We will have a n. N is nothing but the length of the permutation p. So this will be a permutation. Let's say if we have a 2, our only permutations are 1 2 and 2 1. Similarly for 1 for 3 1 2 3 1 3 2, like this. So we will have to construct a permutation p of length n such that we have to minimize the sum of the minimum values of all subarrays of length k. So let's go reversely. we have subarrays of length k, and what we have to get the minimum values of all those subarrays, and we have to take the sum, and we overall have to minimize that sum. Now let's understand with the example. Before that we have input t and then k and output a permutation, and most importantly we can print multiple answers. There are multiple answers, so we can print any of them. Let's take the example 4 and 2. Our permutation will be of length 4 and our subarray's length, subarray of length k, will be 2. So we will be having subarrays of size 2. So what do you mean by subarrays? Let's just revise them very fast now. So for subarrays of length 2 will be 1, 2, 2, 3, 3, 4. Pretty simple. Now what we have to do, we have to construct a permutation such that the sum of minimum values of the subarray of length k. What is the sum of these subarrays? We have 3 subarrays, and take out the sum of the minimum values. So in this subarray we have 1 as our minimum element, in this we have 2, and in this we have 3. So the overall sum is 6. So this is one of the permutation. What we have to do, we have to find a permutation such that this value is minimized. This value is minimized. So let's see the answer for this, that is 4 and 2 is nothing but 3, 1, 2, 4. In our previous 1, 2, 3, 4 our answer was 6. Let's see why this gives minimum. Our first subarray is 3, 1, that is minimum is 1. Our second is 1, 2, that is again minimum is 1, and then we have 2. So our sum is 4, which is less than 6, and we cannot have lesser value than 4 in this permutation of length of 4. So how we achieve this 4? If you see, just compare these subarrays. What happens in the minimum values of these subarrays? In 1, 2 we get our minimum 1, that is equal to this, but in this our minimum value changed to 2. But here, because our 1 was in between these two subarrays, our minimum value remains 1 here, but here it changes to 2. Again, in the last subarray our minimum value changed to 3, but in this, because our 2 was present in the last subarray, our value was lesser than 3, that is 2. So you can understand, if we place our minimum values in the between or the intersections of maximum subarrays, like in this what we did, we placed the 1 in 2 subarrays, intersection of 2 subarrays. Similarly, at the last subarray we could not put a 1, but we put the next minimum element of 1, that is 2. This is more over the logic. Now let's take one last example, that is 8, 3. So we will develop a logic for this question then. For 8, our subarray length is 3. Our answer is 4, 6, 2, 8, 3, 1, 5, 7. What happens when we choose this subarray? Our minimum is this, in this still this, and in this still this. So these two covered these 3 subarrays because it was in the mid of this whole subarray. In the next subarray, what happens? From this till this we got 1, from this till this again 1, and from this till this again 1. So if you understand, the only contributing elements are 1 and 2 here, and as they are placed in such a way, we get the minimum sum. So let's understand how they have been placed. and we do not care about all the other elements that do not contribute. So we can put them any combination. That's why our answers are multiple and we can print any of them. We just matter the minimum, the position of the minimum elements that contributing. So let's see, this is the indexing. For n is equal to 8, I guess, okay, for n is equal to 8 and k is equal to 3, what are the positions of our minimum element? So for this we have 3 and then 6. So our minimum elements are on 3 and 6 that are contributing. What happens for 6 and 1? Let's take 4 and 2. 3, 1, 2, 4. Our minimum element is 1, that is on 2, and then we have 4. It doesn't matter if our answer was 3, 1, 4, 2, because it still gives the same answer. But what if we get 2 on our 4? So here you can see the pattern. For 3 we got 3, 6, for 2 we got 2, 4. So here we have to place the minimum element such that they are on the multiple of k, because they will be present in the maximum number of subarrays. Like 4, 6, we can place 1 here, our first minimum, because the k is 3, multiple of 3 will be 3 first, then we can put any of them here, then we have to put 2 here on the 6th, and we can put 8. If we had the n is equal to 3, n is equal to 9, then we should have put the 3 here, so that it can cover this remaining subarrays of length 3. So what we have to put? We have to put the minimum elements in such a way that they are on the position of multiple of k. So this is for indexing 1. Now let's see code to understand it better. So my code is in zero base indexing. So what I have done, just taken the input t and k. Our minimum element will start from 1, so I initialize my num to 1, and our answer is nothing but a permutation of length n. For one base indexing, I have taken n plus 1 sized array, and I have initialized to -1 first. All elements are -1. What I have done, I have inserted all the permutation in a multi-set. So our multi-set will have like this if our n is 6. And what I have done, I have put the minimum element starting from the k. K is nothing but the multiple of first k will be the first multiple of k, that is k itself. And I have incremented my position with the next multiple, that is nothing but I plus is equals to k. So after 3 plus equal to 3, that is 6, the next multiple. And what I have done, I have initialized that position with our first num, that is num, and after that I have increased, because I have used 1 here, so I have increased my num to num plus plus, that will be the second minimum. And what I have done, I have removed those elements that I have used from the multiset. And after I have done all this, we have to place all the remaining positions that are not multiple of k. So for that, if our element is not if our element is -1, that is we have not put any element on that position. So that time what I have done, I have started putting the numbers from the multiset. This does not matter, but I have the logic behind this is, I have removed all those used, and which are not used can be placed at any position, but you can put it from sorted order as well, that can be counted as well. So that's why I have used multiset for those unused elements to put on the non-multiple of case. So this is overall the logic, and then I have printed the V. So let's take a moment to see how that code works. Let's take if we have 12 as n and 5. So our 1 should be present at 5th, then 10th place should be acquired by the 2nd, and something like this. So these two will be mattered the most. The 1 is here on the 5th position, and 2 is on the 2 is on the 10th position. And I have just, all those are not multiple of k, are arbitrarily placed, but I have done this in sorted order because I have used multisub. So this solution is already accepted. So I guess this much is clear. Now let's move to the third question. So this is a pretty interesting question. So let's understand the logic behind it. This question gave me a tough time in the contest due to very small changes in the problem. So it happens. So let's see. We have Kevin discovery binary string S that starts with 1. This is important. We have a binary string that starts with 1 in the river at Moonlit River Park and handed it over to you. Your task is to select two non-empty substrings, non-empty S, which can be overlapped to maximize the XOR value of these two substrings. We have to maximize the XOR value. What do you mean by XOR? This is nothing but bitwise XOR operation. That is, if we have 1 XOR 1, we get 0. That is, if we have same number, we get 0. If we have different number, we get 1. Basic bitwise XOR operation. The string you choose may have leading zeros. Again, we have test cases. A binary string starts with 1, and what we have? We have to print 4 integers that are nothing but, we have to choose 2 substrings starting with index L1, ending with R1, again second with L2 and R2. In case the 2 substring you selected that starts with L1 and ends with R1, starts with L2, ends with R2. If there are multiple solutions, print any of them. So what we have to achieve here, let's take this example 1 0. Okay. Let's take 1 0 1 0 0 0 0 0. This example, what we have to achieve, we have to select a substring, 2 substrings that are non-empty, such that their XOR value is maximized. If we select 0 and 0, 2 substring, our XOR value is 0. If we select 0 and 1, 0 and 1 will give 1. But as if you see what we have given, that our binary string starts with 1. So what if we have 0 here? Our string does not matter what is here. Our string will start with 1, which is the most significant bit set to 1, which will lead to a maximum value. So what we have to achieve is get the ones at the MSB. This is most significant bit. Starting with most significant bits, we have to make them 1. So how we can make them 1? So for this particular integer, or the sequence of ones and zeros, to make this bit 1, we have to get 0 here. To make this bit 1, we have to get 1 here. Similarly, we have to get this string to make all the bits 1. That is the maximum possible answer for a string of size 4. But those two substrings should belong to the S itself. This is a S itself, but this 0 1 1 1, or if we remove the leading 0, 1 1 1, does 1 1 1 present here? No. But what is the answer given for this question? So for this, answer is given, that is 1 2 3 and 1 to 4. 1 to 4 we have here. 1 to 3 is nothing but 1 0 0. So we have 1 0 0. That is our answer. Why? Because MSB should be prioritized to get 1. We got 1 here, we got 1 here. But because we did not had 1 1 in our string, or 1 1 0, or 1 0 1 1 1, we could not get a 1 here. So that's why we have to be satisfied with our 0 here. Again, we did not have any 1 0 1 type of in our S, so we had to satisfy with 0 here. So moreover, the logic is we have to make the MSPs 1 as much as we can. So if we see, as our binary strings start with 1, if we take 1 to n as our first, that is pretty optimal choice. But if we select for our second, this 0 means nothing, we can place nothing here. So even though if our string, the second string, is of length n minus 1, we can still get the minimum value 1 0 0. That is, this will be considered as 0, and we will get our most significant bit set. The only thing what we have to do is check for the remaining MSPs, if we can make 1 as much as we can. So for that, what we can do, let's take another example, 1 0 1 1 1. For this, to make this set, we should get a 0 here, 1 here, 0 0 0. The ideal string should be 1 0 0 0, but we don't have a 1 0 0 0. But what we have, which is the similar, most similar substring to 1 0 0 0, that is this, that 1 0 1 1, because these two that are most significant bits are similar, but after some point we don't have, but still the answer is nothing but 1 0 1 1 0, and then instead of this we get the most similar to that, that is 1 0 1 1 1 0 1 1, and we get our answer as this. So for this string, what we got from 1 till 2 3 4 5, 1 to 5 is our first substring, that is fixed, and for second what we got, 1 to 4, that is the answer here, 1 to 5 and 1 to 4 for this substring. So I guess moreover the logic is same. So how to find out the similar substring present for that string 1 or the substring 1? So what we can do, we can make a ideal substring. For this, our ideal substring would be 0 0 0 1 0. So we have to find out if 10 is present or not. 10 is present already here, so we can directly get this. We put our answer as 1 to 5 and 3 4. That is the answer here, 1 to 5 and 3 4. So we have to check for the ideal substring starting from left to right. Why left to right? Because left we have MSPs and we go till LSP. So let's go to the solution and let's understand it from there. So first what I have done, let's take the one important example here, that is 10111 10111. What I have done, this t is nothing but our ideal string. Our ideal string is nothing but, in this case, 101000, but this 0 is leading, so we don't have to take it. We just have to search for 1000. So what I have done a flag. If we have encountered a 1, that means all the leading zeros should not be present in that. If our flag is 0, then only we have to put the zeros in our ideal. This gives the ideal string. And then let's take the first example where our ideal is nothing but 111's ideal is 000. All are leading zeros. We don't have a 1 here. So our string will be empty. So our ideal is nothing but empty. In this case, our the first string is still 1 2 3, but our second is empty, and that should be handled because we don't take empty strings. So at that time, we have to take the last only element, such that we get a maximum value and with a non-empty substring. So if our ideal string is empty, that is size is 0, we have to take 1 till n and then the last element. So if our ideal string is not empty, that is this case, that is 1000. In this case, we have to find out the most similar string present in S to T. How we have achieved this? I have used STL for this. We have taken a temp string that is empty at the start. Our first substring is already fixed, that is till 1 to n, and we have to find out L2 and R2. So until we get full our ideal substring, I have started pushing the values of our MSPs till LSP in the temp. That is, first we will get 1. We will search if our 1 is present in our S or not. Is 1 present? That means not equal to n pos. This is nothing but last position. So this means we have found out. Let's get to this condition later on. If we find out, we store the index of that in our L2. So for this 1, we will get 1. It will be stored 1. L2 will store 1. After that, again we push 0 here. Do we have a 1 0 present? Yes, we have. So our 1 0 is present, so our L2 is again remaining at 1. Do we have 1 0 0? No. In this case, it will not get any. So at the end of the string, what we have as L2? That is nothing but 1. It means we have a starting position, but we have to take 1 till R2. What is our R2? R2 is nothing but our ideal string's length, which will be the most similar. So our starting is 1 0, that has been taken, but in reality what we have taken? 1 0 1 1. So this is nothing but the length is 4 fixed. So starting from 1, we have to take total 4 elements. So this is nothing but from L2 plus the t dot size that I have done, temp dot size, same. What I have written +1 here for 1 base indexing, because this gives you 0 base indexing. So what is this case? So because of this case, I suffered a lot in the contest. So let's understand why. So if we take this test case, what happens? That is 10011. 10011. Our ideal is 1100. Now we will start finding out if 1 is present. Yes, we get this. Again 1 is present, 1 is present here. So at the end of the iterations, we could not get after 110, we don't have 110. So our L2 has the value as 4. But can we put after 4, our answer is nothing but 4 and 4 plus temp size, that is nothing but 4 plus 4, that is 4 to 8, that is nothing but 4 to 7, 4 6 4 5 6 7, that is 4 values. So if you see, our last index is 7 and our size of n is 5, so it is out of bound. Because we took from the last, we don't have any values here, so it is out of bound. That's why it is not valid 4 to 7. Instead of that, if we could have just only this, which is most similar, 1 for 1, we had multiple options, this one, but when we get another one, we got this, but this is not valid because after adding temp dot size or t dot size, it is out of bound. So we don't want that. So that's why I have put the condition if whole string is less than n, then only we can take it. So in this case we cannot take it 1 1. So at the end we will have L2 as this pointer only. Then we will take 1 till 1 plus 4, that is 5, that is nothing but 4 minus 1, 4, 1 till 4, 4 elements. So this was all about the implementation of this logic. So it was a pretty good question considering the observations and use of STL. So there are multiple approaches for this question. There is also a mathematical approach. So I have used this implementation of STL. So I hope this question is clear. Now let's move to our last question, that is D. So this seems a pretty big question, but yes, it was a pretty big implementation as well. So it is a pretty good question. Let's understand. Kevin used to get into Rio's memories, and in Rio's memories a series of contests was once held. A series of contests was held. Kevin remembers all the participants and all the contest problems from that time, but he has forgotten the specific rounds, the distribution of problems and the exact rankings. There are m problems in total, with ith problem having a difficulty of bi. Let each contest consist of k problems, resulting in a total of floor division of m by k. This means you select exactly m by k multiplied by k problems for the contest in any combination you want, with each problem being selected at most once. The remaining m mod k problems are left unused. For example, I know this sounds a lot, but we will figure it out. If our m is 17 and we have 3, k as a 3, which means the number of problems in each contest is 3, which means we can have 5 contests consisting of 3 problems each, but we have left with 2 problems that are unused. So there are n participants in the contest, with Kevin being the first participant. Kevin being the first participant. The ith participant has a rating of AI. During the contest, each participant solves all the problems with a difficulty not exceeding their rating, which means if their rating is 400, they can only be able to solve rating problems with a rating less than or equal to 400. Meaning, the ith participant solves the jth problem if and only if AI is greater than or equal to bj. In each contest, Kevin's rank is 1 plus. This is important statement. Understand this. Kevin's rank is 1 plus the number of participants who solve more problems than he does. That is, let's see if we have three people here. Let's take Yash, Harsh, and Vishal. Let's see, we have five problems. And okay, we missed Kevin. How can we? We have Kevin as well. So what happens? In one contest, Yash solved three questions, Harsh solved two questions, Vishal solved two questions, and Kevin also solved two questions. So let's say Vishal solved four questions. He is intelligent. So what will be the ranking? Obviously Vishal will be first, then Yash. Now, who will be the first? If is Harsh or Kevin? Kevin's rank is 1 plus the number of participants who solve more problems than he does. So the only people that solved more problems than Kevin is Vishal and Yash, and he will be placed 1 plus after them. So after Vishal and Yash, we will get Kevin, and after that Harsh will be at the last. Which means, let's understand is as a analogy to our code forces, which means Kevin is the fastest to solve n problems. That's why his rank is above. So let's move ahead. For each k 1 till m, Kevin wants to know minimum sum of his ranks across all m by k contests. In other words, for some value of k, after selecting the problems for each contest, you calculate the rank of Kevin in each contest and sum up this rank over all m by k contest. With your goal is to minimize this value. Okay, this is a lot of theory, lot of big paragraph. So let's move to the directly to the test cases. So understand. We have n and n, number of participants and number of problems. Our A array has rating of each participant, B has difficulty rating of each problem. First we have 4 and 4. 4 and 4. Our ratings of our people are 4, 3, 7, 5, and the ratings of our problems are 2, 5, 4, 6, and the first participant is Kevin, which means Kevin's rating is 4. So let's see, we have to take k problems starting from 1 till m in one contest. So our first contest, or the contest with problem 1, we will get 4 contests. So let's understand, our Kevin's rating is 4, and what they have said here, when k is equal to 1, since each contest only contests one problem. So we will be having 4 contests because we have one problem in each contest. So 4 problems divided by 4, we will have one problem in each contest. Okay. For example, in the contest which only includes third problem, which has difficulty of 4, all participants except the second can solve it. Since no one solves strictly more than problem than Kevin, his ranking in this contest is 1. So let's understand this condition. We have a contest and the only problem that has is of rating 4. So Kevin is having rating 4, so he can solve. This person will not be able to solve. This person will solve, this person will solve. So let's say this was Yash, Vishal, Harsh and Kevin. So Kevin solves it, Vishal solves it, Yash solves it. So Kevin being the fastest among them, he will be ranked 1 because no one has solved more problems than him. All has solved one problem except this. So he will be at the last rank. So if we take this 2, this will be solved by everyone, but still Kevin being the fastest, his rank will be 1 for this question, for this question as well. But if we take 5, Kevin won't be able to solve this question, but these two people will. So Kevin's rank will be after them. So Kevin's rank will be 3. And for 6, he won't be able to solve, he won't be able to solve. The only person will be Vishal, so his rank will be 2. And we have to take sum of this. So our sum is 7, that they have said. So this is for k is equal to 1. Now we have to find it for k is equal to 2 till k is equal to m. This is the question. Now let's move to this question, but our k is increased to 2. 4, 3, 7, 5. 2, 5, 4, 6. Our k is 2. So only the number of contests will be 2. So one optimal way is to choose first and third problem from a contest, and second will be for second and fourth for another. If we select 2 and 4, Kevin will be able to solve both the questions, so his rank will be 1. But when 5 and 6, what happens? Kevin will solve 0, this will solve 0, this will solve 2, this will solve 1. So Kevin's rating will be 3. Kevin's rank will be 3. So moreover, the sum will be 4. So we have to lower the sum, this sum, for every k. What happened here? To minimize the sum, which means we have to make the rank of Kevin lesser. So for this contest 2 and 4, we got rank 1, but for that we got 3. So as greedy logic, what we will do, we will make groups of k that are lesser or equal to Kevin's rating. At that time it will give ranking 1. But let's take another example that will lead to a minimum value, but we have to make changes such that we get a good rank for Kevin. So let's take this example, 50486. So what happens for 13927? For 1, Kevin's rating is 5. So for 1, rank will be 1, 1, 1. For 9, no one be able to solve. So here also rank will be 1. For 7, the only person will be this. So total rank will be 1 plus 1 plus 1 plus 1, that is 6. Yes, our answer is 6. But when our k is 2, yes, we select like if we sort it like this, these two will be solved by Kevin. So for this contest its rank will be 1 for this contest. So understand, for this contest what happens? For 3 and 7, this person would be able to solve 2 questions. So Kevin's rank will be 2 if we select 7. But if we select 3 and 9, the 3 will be solved by Kevin as well as the person with the highest rating. But as we have selected 9, no one can solve this question. So still, because of that, Kevin is at number 1. So what happened? After a point, we started taking the maximum rated problem. And what is this point? This point is when Kevin could not solve the question, which means the problem has rating greater than Kevin's. So the optimal choice to choose is nothing but 1, 2, 3, 9, 7 in this order. correct? So this is more over the logic for this question. What we will do, we will sort the problems in such order: 1 1 1. Let's take 1 3 4 5 6 9 8, and we have our Kevin's rating as 5. So we have to make a combination of the problem array such that after 5 we will start taking the maximum rated questions. So till then our array will be this, but after this point, because the Kevin's rating is lesser than the problems, we will start taking them in the reverse direction so that we can achieve the lesser rank for Kevin, so that no other people can solve the questions. So this is the greedy method to get the optimal choice of the sequence of the problems. Now how to implement this? So till this we will have our Kevin's rank as 1 till this. After that it depends how many person can solve this question. So for this example 1, for this 8 2 people, for 6 3 people, and depending on this number of people can solve, its Kevin's rating will be just nothing but +1, as they have said. So let's understand the code, and then the logic will be more clear. I have taken NNM ratings of the player, problem ratings. Kevin rating will be the rating of 0. Then I have sorted both the arrays in ascending order. But what I have done here, after some point, that is 13927, let's take this 13927, and our Kevin's rating is 5. When there is a problem with greater than Kevin, we stop the index. The sorted array will be this. After this we get a 7, which is greater than 5. So we stop here, our index will be pointing here, and we break. And what we do, and then we reverse in descending order. Problem dot begin plus idx till end, which means we get our array as this. Now to get to know how many can solve the problem with rating 9 to get the rank of Kevin, I have used a frequency vector, that is count the number of people that can solve the question with rating 9. So starting with index this, what I have used, I have done lower bound, that is nothing but binary search. This will give me if our people are of rating 10 and 11, for 9 they will get answer 2, for 7 again 2. If we have people with 6 10 11 or 7 10 11, the problem with rating 9 will be solved by 10 and 11. So we have for 9 2 people can solve, for 7 all 3 can solve. So we get the frequency of those problems with this logic, that is by using lower bound on the ratings. And then we have our answer, as we have to get a for every k from 1 to m, starting with 1 to m, our first sum is initialized with 0. Now let's understand this part. 1 2 3 4 5 6 7 8. Let's take after this point, we reverse the array. 7 6 5. Now let's see if our k is 3. So for 3, I will, as our array is sorted, we will see if the rightmost is solvable by Kevin or not. Yes, let's say the Kevin's rating is, let's say 4. For this 3, it is lesser, so Kevin will be first. problem j is less than or equal to kv. Yes, it is lesser. So its rank will be 1 for this subarray or the segment. After that, what I have done, this is just for the one base indexing, and then I have jumped jumped with r, that is nothing but jumped with k. I have jumped from 3 to 6 now because I am considering this segment now. Now I will check if 6 is greater than 4, so we cannot have some this. But what we will do, we will add the ranks of the people which can solve 6. So 6 will be solved by count of j plus count of j, which is taken from here. So after that, the rank of the game will be +1, and after adding all these ranks, we get our answer I in this answer sum in the ith index for k, and then I have printed the answer. That's all. I hope the logic is clear. It is a pretty complex problem. Just implementation was needed, and 2 observation. The first observation is for the reversing after IDX. This is a pretty greedy observation, and the second one is to optimizing this. So I will show you my submission where I got TLE because I used brute force there. So in this, if you can see that to get the count in the map, I have used from IDX j of n. So this was brute force approach, but as our arrays are already sorted, we optimized the count to get the count using binary search. So this was overall the question. I hope all 4 questions are clear to you. If you guys have any doubt, put down in the comment section. I will try to address your doubt as well. So thank you for watching. Goodbye.